I used to have this very romanticized view of coding. I'd watch movies where the hacker is in a dark room, green text is cascading down the screen, and they're just typing furiously like they're playing a piano concerto. It looks like they're casting spells. It looks like magic.
And let me guess, now that you've looked under the hood, the magic is gone.
Completely. I've been reading through this lecture on variables, operators, and modularization, and I've realized something profound. Programming isn't magic. It is bureaucracy. It is aggressive, hyper-specific, neurotic organization. It's not casting spells. It's filling out forms in triplicate so the computer doesn't burn the house down.
That is honestly one of the best definitions I have ever heard. You are absolutely right. We tend to think of computers as these super intelligent brains, but at the fundamental level, the level we are discussing today, they are incredibly literal and incredibly fragile. They need structure or they collapse.
And that is our mission for this deep dive. We are taking the source code, pun intended, of this lecture and stripping it down. We aren't just memorizing syntax or commands. We are going to figure out the grammar of how a computer actually thinks. We're going to look at the atomic units of data, the weird ways computers do math that would make a math teacher cry, and finally, how to organize a massive program so it doesn't turn into a digital disaster.
Right. We are moving from the micro, the single variable, to the macro, the architecture of the whole system.
So let's start at the very bottom, the variable. The source material defines a variable as a named memory location whose contents can vary. But let's get physical for a second. When I write x equals 10 in my code, what is actually happening inside the machine?
Physically,
Yeah.
you are making a reservation at a restaurant. When you declare a variable, you are sending a signal to the operating system saying, "Excuse me, I need a specific block of random access memory RAM, and I would like to reserve it for my exclusive use. Oh, and I'm going to name this table X."
So it's a specific address on a specific chip.
Exactly. And the variable part means it's an open table. You can see the number 10 there, then 5 minutes later you can kick 10 out and see the number 50 there. It's a temporary holding space.
Okay, that makes sense. But the source material immediately pivots to this concept of a constant. And this is where I got a little stuck on the philosophy of it. If the whole point of a computer is to compute to process change, why would I ever want a variable that cannot vary?
Think of it as a safety rail. Let's say you are writing code for a bank. You have a number representing the current interest rate. It's 5%.
Yeah.
You do not, under any circumstances, want a bug in line 4,000 of your code to accidentally overwrite that interest rate with a customer's account balance.
That would be a very bad day for the bank.
A catastrophic day. So you use a constant. You are telling the computer, take this value, put it in the box, and then weld the lid shut. You are locking it down so that neither you nor your teammates can break it by accident.
I noticed in the reading that different programming languages seem to have very different personalities when it comes to this welding process.
Oh, absolutely. It's a cultural thing. Languages like C++ or Java are very strict. They are these strict librarians of the coding world. C++ uses the keyword const. Java uses final. If you try to change a final variable, the code literally won't run. The computer stops you and says, "You signed a contract, you can't change this."
And then there's Python.
And then there's Python. Python is the cool substitute teacher who lets you sit on the desk.
It's just an honor system, right?
Pretty much.
Yeah.
In Python, there is no weld. The convention is that if you want a constant, you type the name in all cap BS. So if you see tax rate written in capital letters, that is the programmer screaming at you, "Please do not touch this."
But the computer doesn't care.
Not at all. The computer will happily let you change it. The all caps is just a signal to other humans to respect the boundaries.
I love that. I'm yelling at you with text, please respect my life choices.
Okay, so we have our memory boxes. But here is where the bureaucracy kicks in again. You can't just say, "Computer, hold this." You have to tell the computer exactly what it is holding. This is the data type ecosystem. And this is crucial because computers are misers. They want to be efficient. They need to know exactly how much RAM to reserve. You don't need a shipping container to store a pair of sunglasses.
Let's walk through the big ones mentioned in the source because I think the context here is fascinating. We start with the numeric types. The heavy hitter is the integer.
The humble int. This is the standard for whole numbers. No decimals allowed. In most modern systems, an integer takes up 4 bytes of memory. That's 32 bits of ones and zeros.
And the source mentioned that 4 bytes gives you a range. It's roughly negative 2.1 billion to positive 2.1 billion. which sounds like a number so big you'd never need to worry about it.
You would think so, but that 2.1 billion limit is actually a ticking time bomb.
Wait, really? Is this like a Y2K thing?
It's exactly like a Y2K thing. It's called the year 2038 problem.
Hmm.
See, many computer systems track time by counting the number of seconds that have passed since January 1st, 1970. They store that count in a standard 4-byte integer. Well, in January of 2038, that counter is going to hit 2.1 billion. It's going to hit the limit of what an integer can hold.
And then what happens?
Depending on the system, it might crash, or it might flip around to negative 2.1 billion, which would make the computer think the year is 1901.
So because we chose a standard box size 50 years ago, we have a deadline coming up.
Exactly. That's why understanding data types matters. If you're planning for the long term, int might not be big enough. You might need a long, which is 8 bytes, and gives you a number so big it's effectively infinite for human purposes.
That is wild. Okay, moving on from whole numbers, we have the messy world of decimals. The source breaks this down into float and double. Now, to the untrained eye, these look the same. They both hold decimals, but the expert advice here was pretty stark.
It comes down to precision. A float is small 4 bytes. It's fast, but it's fuzzy. It's only accurate to about 6 or 7 decimal places.
Fuzzy is not a word I generally want to hear when I'm doing math.
Well, context is everything. If you are programming a video game and you need to track the position of a particle of smoke, float is perfect. If it's off by a millionth of a millimeter, nobody cares. It saves memory.
But if I'm calculating the trajectory of a SpaceX rocket,
Do not use a float. You will miss Mars by 1,000 miles. You need a double. It uses 8 bytes, double the memory, but it gives you 15 to 16 digits of precision.
okay, here's a scenario. I'm building a banking app. I'm handling people's money. Double is the way to go, right?
Actually, no. And this is a huge trap.
Really?
You should never, ever use floats or doubles for money.
Why not? A double is precise to 15 digits.
It's precise, but it's not exact. Computers count in binary base 2, humans count in base 10. There are some numbers, like 0.1, that you cannot represent perfectly in binary. It's like how 13 is 0.333 repeating forever in our math. In binary, 0.1 is repeating decimal,
So there's a tiny error.
a microscopic error. But if you're a bank processing millions of transactions, those microscopic errors start to add up. Pennies start disappearing or appearing out of nowhere.
It's literally the plot of Office Space. They were stealing the fractions of pennies.
Exactly. If you use doubles for banking, you are accidentally writing the code for Office Space. For money, you have to use special data types, usually called decimals, that handle the math differently. But for general science, double is your friend.
Good to know. Don't use rocket science math for my checking account. Let's jump to text. Char versus string. This seemed a bit pedantic in the notes, but apparently getting this wrong causes a lot of headaches.
It's a syntax trap.
Yeah.
A char is a single character, the letter A. It takes up 2 bytes because it supports Unicode, so it can be a character from almost any language. But the rule is single quotes. You have to wrap it in single quotes.
And a string.
A string is a sequence, a word, a sentence, a paragraph, and it must use double quotes.
So if I type the letter A inside double quotes,
The computer sees it as a string that just happens to be 1 letter long. It treats it differently in memory than a char. It's like the difference between a single sheet of paper and a notebook that only has 1 page written on it. They're different objects.
got it. And finally, the tiniest box of them all, the Boolean.
The logic gate. True or false? Yes or no? 1 or 0?
The source noted that often, under the hood, 1 is true and O is false.
Yes. In the early days of C, there wasn't even a Boolean type. You just used integers. If the number was 0, it was false. If it was literally anything else, the computer assumed it was true. It's the simplest form of data there is.
So we've built our boxes, our variables, and we've chosen the right size, the data types. Now we have to label them. And this section of the lecture made me laugh because it seems like programmers treat naming conventions like a fashion show.
It really is. The computer does not care what you name a variable. You could name a variable Spaghetti Monster, and the computer would process it just fine. Naming conventions are entirely for the benefit of the human beings who have to read your code later.
Let's run through the looks mentioned in the source. First, the Python style. Snake case.
Snake case, all lowercase letters separated by underscores. My tax rate. It's low to the ground. It's very readable, like a sentence.
Then the Java and JavaScript standard. Camel case.
Camel case. You start with a lowercase letter, but the beginning of every new word gets a capital letter. My tax rate. It has humps.
And then the one we mentioned earlier, the one that looks like shouting. Screaming snake case.
Also called macro case. All caps with underscores. As we said, this is the universal sign for I am a constant, do not touch me.
But there are some hard rules, right? It's not all just style.
Correct. Two big ones. First, no spaces. You can never name a variable my variable with a space. The computer thinks that is two different commands. And second, you generally cannot start a variable name with a number. First place is an illegal name. Place 1 is fine.
I want to pivot to a specific horror story mentioned in the source material. It's about what happens when you create a variable but you forget to put anything in it. The uninitialized variable.
Ah, yes. The ghost in the machine.
So I declare a variable. I say int my number. I've reserved the memory, but I don't assign it a value. I don't say 5 or 0. I just leave it.
Right. You've reserved the land, but you haven't built the house.
And the source has this example where they print out the value of that empty variable, and the output is this garbage string of numbers and symbols, like 23423 at $. It looks like the computer had a stroke. Where does that come from?
It's not actually garbage. That is the scary part. That is data.
What data?
It's whatever was happening in that memory slot 5 milliseconds ago.
No.
Maybe it's a fragment of a photo you were looking at. Maybe it's part of a text message. Maybe it's a piece of code from your web browser.
Wait, so the computer doesn't clean the memory before giving it to me?
No. That takes time. The computer just says, here is address block 400, good luck.
Wow.
If you don't sweep the floor by initializing the variable, setting it to 0, you are effectively stepping into a hotel room where the maids haven't cleaned up after the last guest.
That is visceral and
Yep.
disgusting.
It is. That garbage data can break your calculations. Imagine adding 5 to a fragment of a JPEG image. Your program will crash.
So the rule is always initialize.
Always. Intend my number OB0. Wipe the slate clean before you use it.
Speaking of confusing math, let's talk about operators. Because
Yeah.
there is a trap here that I feel like I would fall into immediately. The equals sign.
The assignment operator versus the comparison operator.
In math class, x phi is 5 is just a statement of fact. But in code, it's a command, right?
It is aggressive.
Yeah.
In code, a single is the assignment operator. It is an action. It says, take the value 5 and shove it into the box labeled x. You aren't asking a question. You are giving an order.
So if I want to ask the computer, hey, is x equal to 5, I can't use a single equals sign.
No, you have to use the double equals equals. That is the comparison operator. That asks the question and returns a true or false.
And if I mix them up, if I write an if statement that says if x equals 5.
This is the classic bug. If you write if x, x5, the computer doesn't check if x is 5. It makes x equal to 5. And usually, the process of assigning a value counts as a success or true result. So the if statement runs, your variable has now been overwritten with the wrong number, and your logic is completely broken.
And the code doesn't crash.
No, that's the worst part. It runs perfectly. It just does the wrong thing.
Right.
You could spend 3 days debugging that and look right past it because your brain reads as equals.
Man. Okay, another thing the source hates. Magic numbers.
Oh, magic numbers are the bane of my existence.
They give this example of a paycheck calculation. Pay equals hours 7.25.15.
Right. And looking at that, I have to ask, what is 7.25? What is 0.15?
I mean, I can guess 7.25 is the hourly wage, and maybe 0.15 is the tax rate.
You can guess, but you don't know. They are just numbers floating in space without context. They are magic. And here's why they are dangerous. Let's say the tax rate changes to 20%. If you use magic numbers, you have to search through your entire program, maybe thousands of lines of code, for the number 0.15.
And hope you don't find a 0.15 that represents a discount on a pair of shoes.
Exactly. If you change the wrong one, you break the store. The solution, again, is organization. You define constants at the top of your file. Const double pay rate equals 7.25. Const double tax rate equals 0.15.
So the math becomes pay equals hours pay rate tax rate.
It reads like English. And if taxes go up, you change one number at the top of the file, and the entire program updates automatically. It's safer, and it's smarter.
Okay, one last bit of weird math before we get to the big picture stuff. The modulus.
To the percent sign.
I haven't used a remainder since 4th grade long division. Why is this a core tool for programmers?
Because it is the best way to detect patterns.
Walk me through the example. 20% 7.
Okay? How many times does 7 go into 20 without going over?
Twice. That gets you to 14.
And what is the difference between 20 and 14?
6.
So 20% equals 6. It gives you what's left over.
I get the math, but why do I care?
Think about a digital clock. When the minutes hit 60, they don't go to 61. They wrap back around to 00. That's modulus 60. Or think about checking if a number is even or odd.
How does it help with that?
If you take any number and do modulus 2, the answer can only be 0 or 1. If it's 0, the number is even. If it's 1, the number is odd. It's an instant switch.
Okay, that is actually super useful. So we've covered the bricks, the variables, the types, the math. Now let's talk about the cathedral. The lecture shifts gears to modularization.
This is where we leave the micro and go to the macro.
The source defines modularization as breaking a large program into small, manageable modules.
Think of it like a book. You don't write a novel as one single paragraph that goes on for 300 pages. You break it into chapters. Modularization is breaking your code into chapters.
And the source outlines a very specific structure for these chapters called mainline logic. It claims almost every program follows the same 3-step heartbeat.
It does. Whether you are launching that rocket to Mars or just playing solitaire. Step 1, housekeeping. Step 2, the detail loop. Step 3, end of job.
Let's break those down. And to do it, let's use the homework assignment from the source, which I thought was hilarious. They ask you to modularize washing the dog.
A classic algorithm.
So housekeeping. In code, this is declaring variables in the dog scenario.
It's the prep work. You can't wash the dog if you haven't found the dog.
Yeah.
So housekeeping is catch the dog, get the shampoo, check the water temperature, close the bathroom door so he doesn't escape.
If you fail housekeeping, the program crashes.
Immediately, you're just standing there holding shampoo with no dog.
Then the detail loop. In a business program, this is processing payroll for every employee for the dog.
This is the actual work. Apply shampoo, scrub, rinse, apply shampoo, scrub, rinse. It's a loop. You repeat it until the condition dog is clean evaluates to true.
And finally, end of job.
The cleanup, toweling off the dog, giving him a treat so he doesn't bite you, putting the supplies away. In code, this is crucial closing files, releasing that memory we reserved earlier so other programs can use it.
And to visualize this, they use hierarchy charts. It looks just like a corporate org chart.
It is. You have the main function at the top. That's the boss.
Correct.
The boss doesn't actually wash the dog. The boss just delegates. The main function calls housekeeping. When that's done, it calls the detail loop. When that's done, it calls end of job.
Why do it this way? Why not just write a list of instructions from top to bottom?
2 reasons.
Yeah.
First, debugging. If the dog is still dirty at the end, I know exactly where the problem is. It's in the detail loop module. I don't need to check the housekeeping. I know I caught the dog. I know I have the shampoo. The problem is the scrubbing. It isolates the chaos.
And the second reason?
Teamwork. If we modularize, I can tell you, hey, you write the housekeeping module. You figure out how to catch the dog. I'll write the scrubbing module. We can work on the same program at the same time without stepping on each other's toes because our code is in different boxes.
So if we look at everything we've covered today, from the int taking up 4 bytes to the naming conventions to this mainline logic, there is a theme here.
The theme is anti-entropy.
Say more about that.
The natural state of data is chaos. It's garbage memory. It's magic numbers. It's infinite loops. Programming is the act of imposing a strict, logical, bureaucratic order on that chaos.
It's not magic spells. It's just really, really aggressive organization.
Precisely. It's about creating a structure where the logic can flow without breaking.
I really like that. It makes the whole field feel less mystical and more achievable.
That's the goal.
Before we sign off, I want to leave the listener with a thought. We talked about mainline logic, housekeeping, detail loop, end of job.
Yeah.
I want you to try to debug your own daily routine using that structure, because I realized while recording this, my code is buggy.
Where's the bug?
I think my housekeeping is failing. I wake up and I jump straight into the detail loop checking emails, doing work without initializing my variables. I haven't eaten, I haven't planned the day, I'm processing garbage data.
That's a common crash. Or maybe you aren't doing end of job. You finish work, but you never actually close the files in your brain. You carry the stress into the evening. You never release the memory.
That is too real. I need to work on my end of job module. I think my RAM is full.
Clear your cache, folks. It helps.
Thank you so much for diving into the matrix, or I guess the bureaucracy with us. We'll see you on the next deep dive.
Happy coding.